Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to talk about inscribed angles in circles. We've already talked about central angles, we've talked about arcs, we've talked about chords, we've talked about sectors. In our very last lesson we covered what a radian is. Now we're adding one more thing, an inscribed angle. We're going to skip the do now and we're going to jump right into our vocab for the day. So an inscribed angle is an angle whose vertex lies on the circle. And whose sides contain chords of the circle. So here our inscribed angle is DEF. The vertex E is on the circle. The sides DE and EF are chords. The intercepted arc. This consists of endpoints that lie on the sides of an inscribed angle and all the points in the circle between them. So if I look at these 2 points where they intersect the circle and all of the points on the arc between those points, that's what we call an intercepted arc. Note that we can find a measurement of an arc, right, in degrees, or we can even find the length of an arc in linear units. But that's what an intercepted arc is. It's where the angle intercepts the circle. We've talked about intercepted arcs with central angles. Same idea. It's where the angle intersects the circle. Subtends. This is a less common word that we're going to use. I am going to throw it at you because you may see it every now and then, but we're not going to use it much throughout the rest of the unit, but we should still know what it means. Subtends is when a chord or arc, when a chord, let me speak properly here. A chord or arc subtends an angle if its endpoints lie on the sides of an angle. So what does that mean? Well, we can have an arc or a chord subtend an angle. So here, DF, the arc, and DF, the chord. So the arc's already drawn there in red. The chord, we'll do that in pink. They both subtend angle DEF. So the intercepted arc, we consider that subtending the angle. And if you also connect those 2 points where the angle intercepts the circle and draw the chord, that can also be said to subtend that angle. Again, not a word we're going to use too often, but I will throw it at you because you may see it in a theorem here or there. Speaking of theorems, we have our first one today, which is going to talk about the measurements of inscribed angles. So the measure, and this is called the inscribed angle theorem, the measure of an inscribed angle is half the measure of its intercepted arc. Let me draw you a brand new circle. That's pretty good. Here's my inscribed angle. Let's say the arc, so we'll do that in red. Let's say this arc has a measurement of, we'll say 80 degrees. Well, that means the angle is going to be 40 degrees. So this is different from a central angle, right? A central angle, let me put this on here as well. Vertex is at the center of the circle. A central angle has the same measurement as its intercepted arc. Right, so central angles have the same measurement. Inscribed angles have a measurement that is half of the intercepted arc. We are going to prove one of these cases. For this proof, for the full proof, you actually have to prove when the center of the circle is on one of the sides of the angle. Right, that would be case A. We can have a case where the center is in between both sides of the angle, and one where it is completely outside. This little asterisk just says that note that the inscribed angle theorem also means that the inscribed angle will be 1/2 the measurement of the central angle that intercepts the same arc. And that's what I kind of just showed you over here. right? That green angle, a central angle, and the pink angle, the inscribed angle, both of those intercept the same arc, right? They both intercept the red arc. So if you have a central angle and an inscribed angle that intercept the same arc, the inscribed angle will be half the measurement of the central angle. Let's go ahead and prove this for one of the cases, though. Let's prove that the inscribed angle has to be half the measurement of the intercepted arc. We are actually going to prove it when, if we look at our diagram here, let me see if I can make this one more tick smaller. There we go. We're going to prove it for when the center of the circle is on one of the sides of the angle. So when one of the sides of the angle is the diameter. So the only thing we're given is that angle CBA is inscribed in circle X. And we want to prove that the measurement of angle CBA is 1/2 the measurement of arc AC. All right, I'd encourage you to pause the video, see how many of these you can get, see if you can kind of understand the proof line by line, and then come back and join us for a discussion of it. Okay, let me center these so are right in the middle. Well, I thought I was going to center those. Let's try that one more time. There we go. First one is given. Second one, it says draw radius XA, so segment XA. I'm going to do that on my diagram. Now, there's no proof for this, right? All we've done is constructed the radius. So what we say here is this step is just justified by a construction. We've just drawn a segment from A to C. If you didn't get that one, that's okay. Our next step says the measurement of angle AXC is equal to the measurement of angle CBA and the measurement of XAB. So what they're saying, if I label these angles, the measurement of angle 1, sorry, I should label it in the right spot. Measurement of angle 1 is equal to the measurements of angle 2 and 3. Well, what theorem tells us that, right? If I take this out of the circle, what tells us that this angle here has to be equal to the sum of angles 2 and 3? Well, that's the exterior angle theorem for triangles. The exterior angle theorem. We've proved that back in a unit previously. Nothing to really put on our diagram there. Whoops. Nothing to put on our diagram there. Next one says segment XA is congruent to segment XB. Well, XA and XB are both radii, so we can just say the radii of a circle are congruent, or radii of the same circle are congruent. There's no specific name of a theorem here or a definition. This is just a fact, right? It's actually part of the definition of a circle, right? That's how we build a circle, is we take a point, we take a radius, like 2 inches, and we just extend from that center point 2 inches in all directions, right? And if we do that an infinite amount of times, we will start to form our circle. Next one says angle CBA is congruent to XAB. You know what we could do before we do that? That would help us. Put some tick marks here because we just proved that those segments are congruent. Now it may be clear why angle CBA is congruent to XAB. Well, this is the isosceles triangle theorem. If we have two sides of a triangle that are congruent, we know that the angles opposite those sides also must be congruent. All right, then we're saying the measurements of those angles must be equal. Well, that's just going to be definition of congruent angles. Then I'm told the measurement of angle AXC is equal to the measurement of angle CBA plus the measurement of angle CBA. Well, we need to look at these two statements, right? Because they're pretty close, except there's some substitution going on, right, with these two right here. And we're allowed to substitute in CBA for XAB because CBA is equal to XAB. So we substitute it in there, and then that equation becomes this one. Substitution property of equality. Transitive property of equality would actually be incorrect here. Then it looks like we are just simplifying the right-hand side, combining our like terms, the two measurements of angle CBA. Next one says the measurement of angle AXC is equal to the measurement of AC. Well, this goes back to the fact that central angles and their intercepted arcs have equal measurements. Now that's what we're going to write here. Whoops, not in that spot. Central angles and their intercepted arcs have equal measurements. There is no special name for this. We're just going to write it out. Let's look at the next one. It says 2 times the measurement of angle CBA is equal to the measurement of arc AC. Well, they took these two equations, right, and they created this third one. This one would actually be the transitive property, right, because both of these things that I'm boxing in pink are both equal to the measurement of angle AXC, so we can set them equal to, each other. Best answer here is transitive property of equality. And if we divide both sides by 2, division property of equality, we get what we wanted to prove, that the measurement of the inscribed angle, CBA, is equal to 1/2 the measurement of the intercepted arc. Okay, again, this is just proving one case. We'd also have to prove the case where the center is inside of the angle and when the center is outside of the angle. So we have to prove this case as well as this case. But for now, we'll just take for granted that those cases can be proven. Otherwise, this video would drag on out for quite a long time. We do have a couple more theorems to look at, and then we will do 1 or 2 application problems, actually finding some measurements. So let's take a look at this, actually a corollary down here. It says if 2 inscribed angles have the same intercepted arcs, then the angles are congruent. So if we look at the blue and the red intercepted arcs, over here, right? They both share the blue and red angles. They both intercept the circle at arc BC. So they share the same intercepted arc BC, which means those angles are going to be congruent. Now, it's not going to be nicely color coordinated for you in a diagram like that. They're probably going to give you a diagram like this. And we're going to want to be able to tell that there's still 2 angles here that are congruent. These 2 intercepted angles, right? So angle BAC would be congruent to angle BDC. And again, that's because they share the same intercepted arc BC. So we're going to need to pull things like this out from diagrams without it, kind of popping out at us due to colors or whatnot, or congruency tick marks. Second thing we're going to look at is this theorem in the middle. It says an inscribed angle subtends a semicircle if and only if the angle is a right angle. Well, this is kind of just an offshoot of the inscribed angle theorem. Right, if this intercepts the circle and we get a semicircle for our arc, well, we know that's got to be 180 degrees. The arc, we know that the angle has to be half of that. Well, the angle is going to have to be 90. So if your inscribed angle intercepts the circle such that its intercepted arc is a semicircle, well, then you're going to have the angle is going to be a right angle. It's going to be equal to 90 degrees. Last theorem says if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. And this one I want you to think about. Not that you shouldn't have thought about the other ones, but I think this is not as straightforward. Why is that true? Why would opposite angles of a quadrilateral inscribed in a circle have to be supplementary? And let's be clear, right? If I give you a quadrilateral like this, I'm not saying that angle A and angle B have to be supplementary because this quadrilateral is not inscribed in a circle. Being inscribed in a circle means that each vertex lies on the circle. Like that. If there's a vertex that's off the circle, it is not going to be an inscribed figure. So let's think about why it is, though. Why would angles, and we'll look at our diagram down here, why would angles A and C have to be supplementary? Why do D and B have to be supplementary? Think about the theorems we've already covered today in class and see if you could voice it out loud, right? Pause the video and try to explain it out loud like you were talking to someone. Okay, well, if we look at the intercepted arcs, let's look at the intercepted arc for A. Let's draw some better segments on my circle. Intercepted arc AD. Well, that intercepted arc is going to be this arc in lime green, DCB. And if I look at angle C, it's going to be in red. That intercepted arc is BAD. So the measurements of arcs blue and green, right? The measurement of arcs BAD, you could actually just call that BD because it's a minor arc, or it looks like it drawn to scale. And arcs BCD, well, those have to add to 360. So if the measurement of arc DAB plus the measurement of arc B, let's color coordinate this, plus the measurement of arc DCB is equal to 360. Well, I know that the angles combined have to be half of 360. Right, well, so what that means is that the measurement of angle A plus the measurement of angle C will have to equal 180. Right? I don't need to know what those specific measurements are. I just know that their sum for the arcs has to be 360 because it will cover a circle, cover the entire circle. And you could try to sketch out a different quadrilateral, but it's always going to cover the entire circle, both of those arcs combined. Well, then the angles have to be half of that total. Right? So the angles are going to have to be 180, which means they are supplementary. Together, they're going to be 180. Okay, let's apply a theorem or two here to some practice problems. And we'll just do number 1. We'll save the last page for in class. Pause the video, see if you can answer parts A through D, as well as have explanations or work showing how you arrived at your answer. Okay, we're going to start with the measurement of arc SU. Well, I don't know enough of the other arcs to set up any equations, but I do know the measure of that inscribed angle. I know the measurement of angle SRU is equal to 40. So the measurement of angle SRU is equal to 1/2 times the measurement of arc SU. Well, if the measurement of angle SRU is 40, a simple inverse operation of multiplication, right, we'll remove that 1/2, and I will get the measurement of arc SU is equal to 80, labeled on my diagram. Now we need the measurement of angle RST. Well, this time I'm going the opposite way. RST is this lime green angle, and I know what the arc is, right? The arc is 120. Let's do this here. The measurement of angle RST is equal to 1/2 times the measurement of arc RT. So the measurement of angle RST is equal to 1/2 times 120. So that's got to be equal to 60 degrees. Go to 60 degrees right there in our diagram. Done with A and B. Now we need to figure out the measurement of angle RUT. RUT. I'm going to have to draw in a segment here. I'm going to get rid of that green angle. Actually, I'm going to get rid of everything right now that I don't need. So we've got RUT. We have to draw this segment in. Oh, look at that. It has the same intercepted arc as angle RST. Right, that intercepted arc is also 120. So I'm not going to go through all the math again, but it's going to be congruent to angle RST because they have the same intercepted arc. So the measurement of angle RUT has to be equal to 60 degrees as well. Finally, we're finding the measurement of angle UTS. UTS, let us sketch that in orange. UTS. Well, that intercepts an arc of 80 degrees. So we know that that angle has got to be half of that. It's going to have to be 40. You could also think that the orange angle intercepts the same arc as this purple angle. Right? They both intercept the red arc. So those two angles have to be congruent. If I know the purple is 40, the orange has got to be 40 as well. Okay, we will practice the last page during class, but hopefully you know a bit more about how to find the measurements of inscribed angles as well as their relationships to central angles and arcs. That'll do it for today. As always, enjoy the rest of your day, and we will look forward to seeing you next time.